Hello and welcome to a video where we're talking about polymorphism today in C++. I'm going to go ahead and get started with a new empty project, and we're going to be working on polymorphism object concepts in games. I'm going to get started with the way I typically do things by getting the OLC Pixel game engine loaded into my project. Hopefully through seeing some of my other videos, you are familiar with this process by now. With that in place, we'll get our polymorphism CPP file here. Go ahead and define the OLC. Actually, we do this. Grab the example code from the header. Make sure it runs. And we're ready to start talking about things. Excellent. So what are we covering today? Today we're covering the concept of polymorphism and how we can use that to make the code a bit more easy to understand. I think that's one of the key things that polymorphism does. We have this concept of objects, and everything in our game will be represented as some kind of object. And when coming up with polymorphism, we're kind of coming up with a hierarchy. Something that all objects can use or have in common, and then other objects fall underneath those things and use the same common properties. So an object might have a position, in our case. We might also have some kind of image, which represents what to draw on the screen for this particular object. We might have things like specifying what the color of the image might be, maybe a direction variable, and perhaps a speed, right? We want to know what direction they're facing, what their speed might be, what their position is. All objects kind of share these properties in common. The game I'm actually going to be developing today is going to involve having a couple of these enemies just on screen, and we have a player somewhere, and your goal is to simply run over them. Every time you run into them, they will be destroyed. It's a very simple game. All it does is have a little bit of player interaction, have a little bit of collision involved, and then we can see how to structure these polymorphism concepts to use this hierarchy here. The first thing you're going to want to do is set up a struct that everything is going to fall under. And again, we're going to include all the common properties here. So one common property we mentioned was a position. I'm going to represent this using the OLC's 2D floating vector. We also mentioned that every object should have a facing direction and a speed component. This way, the position will essentially be directly influenced by the speed. That's typically how speed works. And we also need an image. I haven't used these before in any of my examples, but today we're going to look at what's called an OLC renderable. And we're actually going to store a reference to it, because unlike storing them in the main game class here, objects are going to want a reference to the images, not the images themselves. If we created an image for every object, then we'd be creating a bunch of excessive images for no reason, when it's going to use the same thing. I do have an asset we can use for this game. It's very simple. Let me see if I can find it real quick. Here we go. I'm going to go ahead and throw that into the polymorphism folder. And I'm just going to put it right here where the CPP and header files are already located for our project. That way we can reference it directly. And if you're wondering what it is, it's a circle, and it's got this representing a facing component. The reason why it's facing to the right is that if you are familiar with angles and radians, then 0 always represents the direction to the right, and it goes counterclockwise up to 2 times pi. So that's why we have it facing to the right already. I'm gonna do... I'm trying to think if there's any other components that are in common with objects right now, but I think this is all we need to get started. And we're not even going to be using direction and speed right away. We're just going to try to get some objects going and build off of this. First thing I'm going to do is hit Control R, and rename this to Polymorphism. This is what I'm going to call the class instead of example. And we're going to make this our polymorphism example. I'm going to get rid of the default draw code now. And I'm going to get rid of this comment here for onUserCreate. So the first thing we want to do is load our renderable. So you'll be seeing that today. This is going to be the player image. And in onUserCreate, we're going to load that image. To load a renderable, there's the .load member. And we have to specify a file name. So I put it in the same directory as everything else, so I just have to type in player.png. And that is all. That takes care of it. I want to use this instead of the sprite or decal pointer setup that I would normally do, because I think this is a little cleaner, and it kind of does all that under the hood for us. Makes it pretty easy to use. Now that we have this, though, if you want to use this, you would type player image dot, and you get access to both the decal and the sprite. These are both functions, so you would specify this if you wanted the sprite, and you would specify this if you wanted the decal. Our objects require us passing in a reference to the renderable, so we'll be doing that next. But first, we have to talk about how we store our objects in here. So, if we had both player and enemy objects, we would want to store them in a vector, like we've been doing for our other game objects, and we'll just keep it a vector of objects right now. So normally what we would do is we would separate this, right? We would have maybe the player as one object, and we would have the enemies as another object. And typically we would even make classes for these, like we would have a vector of enemies, right? In the past, this is what we did. And for player, we would use a player object like this. That's what we've done in the past, but today we're going to be demonstrating why polymorphism lets us do what we do by not even doing this, but smashing the player and the enemy all into one object's array. So for now, we're just going to define it like we've normally done in the past, where we create each object, we define its parameters, it goes into a vector. So for the position of the player, I'm going to set it around 1616. The direction should not be a vector float 2D. That's my bad. The direction should be an angle. So we can say the player will start by facing to the right, so we'll give it a direction of 0, and then we'll give it a speed component of 0, 0. It'll start facing nowhere, or it'll start moving nowhere. And then the renderable itself, we just give it the player image. And once we do that, we've specified all the components of an object, and then we can do the same for the enemies. Notice how I'm not really distinguishing between players and enemies right now. For each of the enemies, I'm going to put them at different locations on the screen. I'm just going to choose random coordinates here. Coordinates that I feel will spread them out decently well. And finally, in onUserUpdate, I'm going to iterate through every object and draw them. I'm going to use the drawDecal function. I'm going to draw them at the position they are located at. So I'm going to use the obj.pos member. And for their decal, each object stores their own reference to a decal. So I'm going to go ahead and grab .image, which is a renderable, and then type .decal to grab the decal specifically. Upon running this, we'll see they've been placed in different spots on the screen, but you see we haven't been able to define what is what right now. They're all just the same thing, which makes sense. We just loaded a vector of objects. Now we're going to start talking about how to differentiate them. We already know both players and enemies need all these parameters. So what differentiates them? What differentiates them is that one is player controllable and one is not. So the first thing I'm going to actually do is define a new Boolean called friendly. If true, this is a player unit. This right here is going to allow us to change it when it's a player. So if I just go back down here and I change this to true, we've now essentially made a player, right? And so if I were to then do something different, like let's say the player can be controllable, right? In theory, if we iterate through all of our objects, I want to separate these for now just so it's a little less confusing. We're drawing stuff down here. Let's handle player input up here. If get key, we can detect keys in the OLC Pixel game engine. We'll detect the right arrow key is held. Then we are going to move this particular object. We'll just adjust the X and we'll add 32 times f elapsed time. This way it moves based on the frame rate. And we can run that. But if we run it and we hold right, everything moves. That's why we made that friendly flag, and I set it to true for one of the objects. So we can say object.friendly is true, that's implied, and we're holding the right key. If those both are true, then the object will move. So we can see just the first one moves now because the first object is the only one that has that parameter. Now you can keep doing this for other things in your game, and everything will just be based on these properties. But there's something messy going on here. You see that in the onUserUpdate function, I had to interrogate what the property of an object was in order to move it. And this doesn't scale very well, because if everything has properties, and I have to check for those properties every time, and we had more than just enemies and players, what if we had coins? What if we had obstacles like walls? What if we had multiple types of enemies? Well, then I have to create all these if statements that say, if it's equal to this, like we have an object type variable, if it's equal to this, we do this. If it's equal to this, we do this. This doesn't scale well and makes it very hard to read your code. Like, I can't tell right away that, oh, this moves the player. Or if there was an else statement here, now we're dealing with moving enemies. Like, that solving this problem involves structuring our objects into classes. So the concept of classes was to make it so we can tidy things up like this. And the most common things we have to do is we have to update our objects based on what's going on in the game, and we have to render our objects based on what's going on in the game as well, and their properties. So I think the way we'll structure this is every object has an update function, right? And this update function will be blank by default. Like, nothing happens every frame we update. We'll just keep it empty. But what we want to do is we want to define some custom types that allow us to change this update function. So if we're a player, then in the update function, we actually want to move with the arrow keys, right? What about an enemy? Well, an enemy might just move around randomly. It'll have some built-in AI. So you'll see that both want to update something, but they both want to do different things. They both want to update in different ways. Okay, so let's try and map that out. So if I create two new structs, and this is what we typically do when we're designing our games, is we separate stuff into structs, that way they're more organized, right? So we got an enemy and a player, and we said we want both of them to have this update function, and presumably with an update function, we're gonna need to know how much frame time has passed from the engine itself. So we'll pass in felapse time, and for both of these, they're gonna do something different. In addition, I will say we'll probably need the engine itself. So I think this is the first time I'm passing in the engine here, but I'm going to pass in the reference to the engine here. And I'm just going to call it PGE because it's essentially the pixel game engine we're getting that from. And the reason why I'm bringing that in is because we're going to want the access to the key inputs, right? So we can say if get key, and we can then specify a key here. So if I'm holding right, again, then for the player, I want to move them. So, you see I'm trying to type in pause here, but I can't. So, unfortunately, I would have to copy and paste this code into here and here. But wait a second. We can use polymorphism to make it so we can inherit these objects into these structs without having to redefine them and remake them every single time. Additionally, both of these have an update function, and both of these look the same. So we can even condense that down too. So in order to create this hierarchy, the first thing I'm going to do in C++ is type a colon and then type object here. What this immediately does is all the properties of object are now also available for a player. So if I type pause now, you'll actually see we can access it. So that's already a big plus for us. But now we have to initialize them. So this is probably the trickiest part of setting up these object-oriented programming like structures in C++ is how do we handle the constructors. So you are going to need a constructor here, and the reason for that is if you want to make this player, you can't make it right now because it can't see these things in the constructor, believe it or not. If we tried to make a player constructor here, and we wanted to define where does it start, right? Where's its position? We're going to need to set it in here, but you'll notice that we can't set the position of directly. We have to call this because it's not, wait, we have to be careful here with the arguments. I called it the same thing, right? So make sure you're pointing to the right object here, and you'll also notice it's complaining that it's a deleted function. And we can keep setting more things here. But yeah, it's a deleted function. And so we have to go back up here to object. And first we have to make a way to define the construction of these objects, because they depend on object themselves. So the construction of object will actually say we define a position, a direction, a speed, the renderable reference, and whether or not it's friendly. And all of that will be set. So we'll put a colon here, and we'll set pause to pause, direction to direction, speed to speed, image to image, and friendly to friendly. So we basically made a quote-unquote default constructor for the object now that we can use in these parent objects. So you'll see here it's still complaining, but now we have a constructor we can use for our inherited objects. So instead of doing this, which doesn't even work by the way, the key aspect here, you'll notice I'm purposely not including the friendly parameter for player, is we can now reference the parent constructor. So if I fill these in, we're now looking at the parent constructor here, object. So we have to fill these in. For friendly, every player is friendly, right? So I don't even need that as a parameter, which is why I omitted that, and I put true here. And I think this is the hardest aspect, like I said, of setting up these object-oriented structures, is how you go about chaining these constructors together. Maybe it'll be a little more clear after I do the object enemy one. So I'm actually going to copy paste this down here because it also inherits object. And for enemies, they're going to use false for the friendly flag. So when we call player, we're calling this constructor here, which is going to call this constructor here to set all of our parameters. Because we can't do it directly as a player because the object hasn't been created yet. Let's go back to the update code. And we're going to add, again, a value to the X position when we're holding right. For the player, we'll also do it for the other directions. So for up, down, and left. And we'll have to change these accordingly. For the enemy, I'm just not going to do anything yet, because now we have to set these up. So we've made an object with a default way to construct it, providing its parameters. We've also made a way to define a player and an enemy. But how do we use these? First, you'll see it's complaining, because before, this right here wasn't optional, since a struct makes all of its parameters optional by default. But we're still creating objects here. This is a vector of objects. Standard objects, mind you. So if I run this, none of the code we just wrote is actually used. And actually it's complaining about other things right now. Yeah, so you'll see here it's complaining that polymorphism is not a class. If we read this from top to bottom, polymorphism is defined up here, but it's needed up here in order to use it. So the easiest way to remedy this is to type this. Class polymorphism exists somewhere. We just haven't defined it yet. And so that will almost make the compiler happy. The reason why it doesn't right now is because these are still references. So you can't use references and stuff from references because they're not... The best way to explain it is that this is called a forward declaration, and it doesn't currently know how to handle this class yet. It doesn't know what its properties are or anything. So as a reference, we can't go around using anything inside of it. We've discovered this in the past with other things too. Especially when I had my multi-file project stuff. That's probably when we most noticed that. So typically we pass these in as a pointer instead, because a pointer is just a set of numbers, and the compiler knows what the size of a number is, so it's a little more happy about doing that. But we still can't access it because a pointer, we don't know what polymorphism contains. So essentially, we've run into that problem where we're going to have to split these into header files. And we've done that before on the channel. I have a video of that if you're interested in seeing how to do that. So we basically have to do that real quick in order to split up our files further. This happens pretty often, and the short-term solution to doing this is defining all of our structs inside of the polymorphism class. That way it knows, hey, polymorphism has these things because it's defined inside of the class. But ideally, you want to structure your project to use multiple files anyways, and usually when you run into these problems where you're passing things via pointers, that's a good time to do so. So I'm going to really quickly go ahead and split up our project into these files now. So I'm going to make a player, an enemy, and an object CPP file. And with all these, we can split up our things accordingly. So first, I'll be following the same process I did when showing off the splitting your project into multiple files video. Is I have an object header and an object CPP file. Usually I copy all of the definitions into here, and then I remove the definition portions and keep only the declarations. So in this case, there are no definitions except for the constructor here, so I will simply remove... Oh, sorry, I'm deleting entire lines. Oops. Delete all that. And then that's gonna go in object over here. I'm gonna have to copy that in a second. Including the header file here will define what an object is, and then including the OLC pixel game engine here will define all these OLC functions here. So now, compiler should be happy, and we've split that up appropriately. It's a little bit wordy, but it will do. Moving on to the player header file. I kind of want to do it this way. Might be easier to see, huh? Because we have kind of longish lines here. So that might be easier to see. So first I'll paste all into player.h. Now we've got a function definition here. So that will definitely be moving into player.cpp. And we've also got a definition or definition here for the player constructor, so I'll be moving that into the CPP file as well. So we can get rid of this, leaving only the declaration, and now we should be good there. Now, it first needs a reference to object, so I'll define object.h here, and then it also needs a reference to OLC pixel game engine, so I'll be defining that as well. Or not defining, sorry, including. And it also needs an include for polymorphism. So you'll see this is the problem we ran into before. Our game engine itself needs its own header file. So we'll be including that as well to make that happy. In the player CPP file, we'll include the player.header, which should define everything here for us and make it happy. And that's good to go. It's still erroring out because right now we need to include polymorphism. We'll get there. And if we include polymorphism.h, we're likely going to include the OLC pixel game engine. So I'm going to exclude it here on purpose because I know ahead of time we're going to be doing that. Let's make the polymorphism header. And now split up our pixel game engine project, which had the CPP file originally. So, Polymorphism.cpp defines a main file. We can leave the main function there. You gotta have a main function in your program somewhere, so that is fine. We have onUser update, onUser create, the class polymorphism, inheriting public or pixel game engine. So first, I'll go ahead and take this entire class here. This was not what we wanted. I still have enemy in here. I'll leave that in here, but I'll get rid of it in a second. And we'll take this part as well. Actually, we'll leave this. Important why we do this, by the way. The polymorphism CPP file needs the its header file. And inside of polymorphism's class, we're going to include the pixel game engine, of course, because it needs it. And on top of that, we need to get rid of the function definitions, leaving only the declarations. Declarations also include the override keyword, so we will define that at least. So in polymorphism, this goes in here and uses bool on user update, like this. You don't include an override keyword when you're doing your definitions of your functions like this. So this is what it should look like in the CPP file. And for the header, we'll get rid of override again. We'll get rid of the definition in the header and leave it only in the CPP file. Like so. Okay. I think we're almost caught up. I hope. So we've also got these two. These are just variables specific to this class. We can leave them like so. And we've also got this constructor. We'll go ahead and make a copy of that constructor inside of the CPP file. Like so. Then we can get rid of the definition of it here. So we've shrunk our polymorphism OC Pixel Game Engine instance into a header file and a CPP file. Finally, it doesn't know what object is, so we have to include the object header here, which will define it. And then the last thing we have to do is move the enemy out of polymorphism. So we'll make an enemy header file. Move this struct out of here into the enemy header file. We have an enemy.cpp source file already, so we know we're going to be bringing in the constructor and the update functions here, adding enemy in front of it. And in the header, we remove the definitions, leaving just those. Finally, it depends on object, and it also depends on the pixel game engine. It also depends on polymorphism, which includes the pixel game engine. So once again, we can remove that include. Enemy.cpp relies on enemy.h. Woo! That was a lot of work, wasn't it? But we finally moved everything out, cleaned it up a little bit. Everything's in multiple files. Hopefully it still works. We're still getting errors, but that's probably because we were still working on the player header when we were doing this. So player relies on pixel game engine. Polymorphism does include pixel game engine, but I think I forgot to, yep. These aren't actually in the player class, so let's define them in the player class so everything gets recognized here. Yeah, we're still working on this, so. What else? We are missing a semicolon. That is true. I agree, there is a semicolon missing over there. So it's linked all the code together. Cool. Happy as can be. we still haven't utilized the player yet. The way I can tell is that, let's go over to polymorphism.cpp. Look at this. This is still a vector of objects, right? So now that we're in multiple files, we're always going to have to reference a different place to see our variables. So our objects is, well, an object vector. Also, is that a red dot? Oops. I guess I never deleted that. So we have a vector of objects still, but we want to be able to say, okay, we want to load a player and 4 enemies. Well, okay, let's try that. Let's try to load a player specifically. The way I'll do that is I'll say, push back a player, and then I will provide the player constructor. So polymorphism doesn't know what a player is, so this is when we include it. Say, okay, I want to use a player now, right? So with a player, here's the parameters. We specify a position. So the player's position will do 16 by 16. The direction will say facing to the right. The speed, we start it as not moving. And a renderable, the player image. This will create a player. And for now, it seems like it's happy with it, right? You think, okay, cool. It made a player. Everything's good. Well, if it made a player, then instead of calling what we wrote earlier to move, we should be able to call object dot and then the update function. You'll see update is not actually in here yet. So the first thing we're going to do is, since every object can have an update function, we need to define an update function. So for the first time, I'm going to be using this virtual keyword. Virtual means that you can override this function inside of a child class. So here we're saying this function update exists, but we're also going to allow it to be overwritten. Every time you add a function, when you have split up files, make sure you add the function in the CPP file as well. So we're going to go over to the CPP file here and add that in as well. We're going to leave it blank on purpose because we want it to be overwritten by other objects. You'll also see it's complaining because I forgot the type. That's important. So here, nothing should have changed, but now if we go back to polymorphism, we can now call an update function, and we'll pass in felapse time. So far, so good? Well, if we call the update function, and the player has an update function, we want to say it overrides it. Now, typing override here doesn't actually do anything. That's not what it's for. But, oh, I forgot we include the PGE too. That's my bad. Let me go back to object.h real quick and add that in. We do want to include that. That's important. And since it relies on the polymorphism class, let's go ahead and include the header for that, which means it includes the header for Pixel Game Engine, so we can kind of remove that just as an implicit add. All right, so it's happy with that. The override keyword isn't mandatory. It will still work without it. The whole reason we do this is, let's say I changed this, right? Suddenly it required a new bool working. Let's say I changed it, right? What the compiler does now is it says, wait a second, you specified the override keyword? There's nothing to override here. This is like a failsafe for you. If you include the override keyword and you change something in the parent class, it lets you know, hey, you're not overriding anything anymore. Check up on what you did wrong. So I highly recommend using the override keyword, even though it's completely optional. It'll save you sometimes. So in player update, we have overwritten objects update, which means in the sense of polymorphism, it will call that instead. So we now have to specify the pointer, to be passed along with the update function. And if polymorphism were to work, then doing this should be valid, and it should call the player's update function, right? Well, first of all, it complains. And why is it complaining? Well, there's a couple reasons for that, but the biggest one is that the vector is not happy with what we've inputted into here. It's saying there's too few arguments, and it doesn't like what we did with the vector there. So, in order to clean this up or understand this right, we have to realize that the syntax for this is completely invalid here. This doesn't let us access objects of other types. With a vector, you're specifically saying objects of only this type can be added here. You can't add a player, you can't add an enemy, you can't do any of that. You can only have objects here. Well, what was the whole point of making all those then if we can't even utilize it that way? Well, one feature of C++ that we can use is by saying this is a container of object pointers. With pointers, C++ has what's called a vtable, and it's kind of like a lookup table that says if you're a player or if you're an enemy, then the lookup table has this kind of back reference, is the easiest way I could describe it, that says, yeah, you're an object. That's how it knows. So C++'s ability to distinguish that from an object pointer allows us to know what the types are based on what an initial object pointer is. So there's some kind of pointer, it's linked to an object, the object is actually an enemy or a player type. And we don't really have to know the specifics of the internals for that system, but this allows us to simply change the vector to hold object pointers, and then suddenly we can use that feature of object inheritance or polymorphism. Unfortunately, by doing this, this changes how we have to approach things, because now we have to create pointers for everything. So first, I have to use the new keyword here to create a new player. And in addition, for all of these, we're going to follow similarly by creating new enemies. So I'm going to type new enemy here. And for new enemy, it's very similar in syntax, if you recall the constructor. Also, we need to include the enemy header file. So with all that in place, that should work. We can just look at the enemy header file real quick. One nice thing I like about header files is that you can go in and look at them and know right away what you have access to. Like you can see at a glance all the variables and such. So that's probably the nicest thing about headers is you don't usually have to open up source files. So we'll refactor the rest of our code here to use this new syntax like so. So now we have player types and enemy types inside of our objects vector, which is now a vector of pointers. So instead of using object references, we're going to switch to object pointers. Instead of using the dot syntax, we have to use the arrow syntax. So we continue to adjust our program so that everything works right here. And finally, we have to look at the object header file, or not object, polymorphism header file. Let's see. Yep. So I already changed to that, so it's happy. This is all happy. It looks like it will work now. But we do have a couple of syntax errors here, so let's take a look. Here it's still complaining about polymorphism, which we'll look at that in a minute. So update does not override any base class. I think this is derived from this syntax error identifier, polymorphism. So polymorphism, let's take a look here, includes object.h, and object.h includes polymorphism. This is what we call a circular header reference. And a lot of times when you get these, all you're going to get is some vague error that says one of these two cannot find the other. Imagine you are the linker. I know that's kind of a weird thing to imagine, right? And you're trying to organize these files and put them into code. You take this block of code here and you put in your program. Here's our program, right? So you insert this block into here. So now this block contains your polymorphism code. You needed to insert this code to then insert all of this code. So now you take all this code, because it included polymorphism.h, and you insert it here. But wait a second. The preprocessor said that polymorphism needed header as well. So since it needed header, you took header and you tried to put it on top. But wait, object needed polymorphism. So you took this block and you put it on top. You see the issue here? They both depend on each other, and it's going to make it very confused and impossible to sort it out. So that's actually why it's complaining. And so what we have to do here is one of these two has to be what's called forward declared. And we can identify that easily by seeing which one doesn't rely on anything from the other. In this case, both don't rely on anything from the other, because in the headers, both of these use a pointer to these. I subtly mentioned earlier that if you only need a pointer as a reference, then you can forward declare them because they don't need to access any of the members inside. They just need to, the compiler just needs to know how large the data is to allocate memory. So we're going to do what's called forward declaring here. And this is usually how you solve these infinite, sorry, not define. Gosh. Class. This is usually how you define these infinite dependencies. We're going to forward declare that somewhere in our program, the class polymorphism actually exists. Polymorphism is not a type name. I defined it, so you should be fine now. Yeah, compiler's being a little dumb. Same with the object. We can just forward declare the object here. And it's one of the few cases we have to do it, but usually if you get these infinite dependency chains, that's what you have to look at. If we're only using the pointers, we can do this in both sides. Getting rid of at least one side makes the compiler happy, but we can get rid of it in both, and we might as well. They both depend on each other. We can just tell the compiler, hey, they will exist somewhere, they're just not defined yet. We also looks like there's some syntax error, maybe? We have a... yes. So it doesn't know how to handle this renderable because that's from a pixel game engine. Remember I removed the include for the pixel game engine because it depended on polymorphism, which had it included? Well, now we can just include the pixel game engine, and that should make it happy. I know these errors are pretty vague and don't actually say this is what's wrong with it, but yeah. Let me move the arrow keys. You'll see the first object moves here because it's defined as a player, and that's actually what we want. And this is really subtle because this is the first time we're seeing this, but if you'll notice, we're not saying if we press the arrow keys, move some object anymore. We're saying call the update function of an object. Well, we go in object.cpp. It calls the object update function, but we defined nothing in it. So this is the magic of polymorphism, is that you have objects updates function, which has nothing in it. So you think, well, it's definitely not running that code because if it did, how's the player moving? But we have a child of object called player who's got an update function. And since it overrides the parent's update function, it has all that code that allows it to do all that keyboard movement. So we override object and run this code instead. And that's what's happening here, because if we go to player.cpp, we'll see here the update function has its own things. So it ignores the object's update function and runs this instead, because the C++ compiler figured out that, hey, since this class override or inherits from object, and we have an update defined, it runs that override. Now what about the enemies? Let's look at the enemies. The enemies actually have something here, but it's blank, right? What if I took this out? Yeah, I'm just gonna simply remove it. What do you think happens now? Do you think it'll complain that there's no update function? Well, no, it doesn't complain. But why? We haven't defined it. We actually have. Enemies are derived from players, or objects, excuse me, right? So inside the object class, well, it runs this update function instead. So we can kind of prove that, because inside of the update function here, let's go ahead and add some code. Update object. And one thing I'm going to do additionally is in the player class, I'm going to say player object. Let me run this. And let me go ahead and pause it. If we look at our output, we get player object and update object 4 times. Player object, update object, player object, update object. Every time we loop through our objects and call the update function for the object pointer, the game or the C++ goes and looks to see if the child objects have an update function. If they do, it runs that one. If they don't, it runs the object's update function. This makes it clear that there is some inheritance going on, and that if there is nothing defined by default, then cool, it works that way. There's also this concept called abstract classes, and I'll briefly go over that now. Let's say we don't want the developer to ever create these objects. In programming terms, this is usually called an interface. An interface is never to be strictly called, it just defines what the structure of child classes that inherit the interface look like. A bit of a mouthful, right? If I were to set this update function equal to 0, which I know sounds weird, right? Set a function equal to 0? What does that mean? Well, that means that we're going to immediately define it as not existing, and this is called a pure virtual function. So a pure virtual function does not need one of these because we defined it as being equal to 0. And what this also means is that now anything that inherits this, so both player and enemy, have to include an update function, and the compiler enforces this. Let's try to run this now. So you'll see it complains, enemy cannot instantiate abstract class. And when it says that, it's currently an abstract class because, and it'll tell you right here, object of abstract class type enemy is not allowed. Pure virtual function, which we just mentioned update was, update, has no overrider. So if you do this, you will guarantee that you'll never create a blank object by itself. You will only be allowed to create classes that inherit that object, and they have to include all the mandatory pieces of it, which we made update mandatory. So inside of enemies header, I'm going to go ahead and now include that because I'm forced to, which means I now have to include update inside of the enemy CPP file as well with all the appropriate pieces to it. And right now I'll just leave it blank because that's, well, we don't have anything to put in it. We were going to make it move randomly, I believe. But yeah, this is kind of important. I wonder why it's complaining right now. I guess we'll find out, huh? Ah, yes, my favorite. I do this way more often than I should. The type. Let's do that real quick. So now here's the cool thing. When we define this timer, I'm going to show you this. Not every object has a timer, right? So objects, very generic. It's now an interface, as we like to call it. Player, cool. Player has custom arrow key movement. It can move using arrow keys. Enemy, though? Enemy is going to move randomly for some amount of time, and then change direction, then change direction, then change direction, at random amounts of time. We need a timer for this, so does a player need a timer? No, of course not. It's not going to use a timer to control this. Does an object need a timer? No, it doesn't either. So in the grand scheme of things, the scope of the timer should only exist in the player enemy, in the enemy class itself. And so when you are defining these, you don't have to necessarily add the timer variable inside of object if you don't need it in there. So in the enemy header file, we're going to define a new move timer, and we're going to set it to 0.5 at the beginning. Inside the enemy's update function, which we know now gets called all the time, we're going to subtract from the felapse time variable, which got passed in, and when it hits 0, or is less than or equal to 0, then that means it's time to update our direction. So we're going to choose a random direction to move in. Remember, we already have a direction variable inherited from the object class. So we're going to randomly choose between one of 4 directions. So we'll do 0 through 3, and then we have to multiply what we get out of that. I'll put parentheses so it's a little more clear what's going on. Multiply that by pi over 2. A full revolution is 2 times pi. So multiplying by pi over 2 means we get it in 90-degree increments. Notice I typed pi instead of 3.14159 here. That's kind of out of habit. You can define a pi constant if you want to, but that's what we have to do. Finally, the direction is already a float that's represented in radians, so this will handle that for us. Once we change direction, we're going to set the move timer to 0.5 again, so that they can move randomly. It might also be the case that enemies and players might want to go out of bounds. We can do that right now. So let's once again evaluate, right? Objects. Can all objects move out of bounds? Yes. Any object can go out of bounds, and we want to stop them from doing that. We want both players and enemies to not be able to go out of bounds. Since this is a global property, we're actually going to change the object file. But you'll notice now, this is a pure function, so we can't just turn it back on. Otherwise, if we try to write some code in the update function, it's going to get overwritten. You can't run the update function of the object code and the update function of the player or enemy code. And I mean, you technically could, but the problem is you would have to call that explicitly in here. I'll show you what that looks like real quick. If we did object : update, and it wasn't virtual, it will actually call the parent function. But from a programming perspective, do you really want to have to remember to do this every time just to have access to that? Not really, right? So we're going to define a new function inside of object that's not virtual, and I'm going to call this the internal update function. Ooh, fancy word. Internal. The whole reason I'm doing this is this function will not be overridable. I'm not using the virtual keyword here. This is only going to be a function available to the object class. And that's intentional. This is something I want to call for every object, but I only want every object to update with this. I do not want other objects to touch this function. So it is intentionally a void function that cannot be overwritten, so it's not virtual. I need to clarify that, that way you can tell the difference between what update and internal update is. Update is just to say, yeah, these are passed on to child classes, do what you want with them, but not this one. So an internal update, our goal is to do a boundary check. So we're going to say, every object has a position. So if the position.x is less than 0, we're going to bump them back to 0. Do not go beyond the left edge of the screen. Same with the top edge of the screen. Do not go beyond that boundary. Finally, the other edges. So if position x is greater than or equal to the pixel game engine screen width. By the way, we don't have access to that yet because we need to include polymorphism here, which object.h does not do, by the way. So that's an interesting point I'll get at in a second here. But we can access the screen width function of the pixel game engine, which tells us if it's out of bounds there. Then set the position x to the screen width. And finally, same for the screen height. Make sure this compiles. It happily does. So the next thing I'm going to do is call the internal update function. There's still no boundary checks yet. So in here, we iterate through every object and call the update function. After we call the update function for every object, we're also going to call the internal update function. Boom, now we've incorporated a boundary check. You'll see the enemies still aren't moving or anything, but can we go out of bounds? It looks like we cannot. So I'm going to go to the right edge real quick. The way I did it, the sprites are not centered right now. And we'll talk about that in a second. But yeah, I cannot go out of the bounds. It's just the moment I press left, immediately I come back. So we know the boundary check is working. It would be nice to center all of our sprites, right? Alright, can you guys figure it out? Where does the rendering code go? Because right now every object just calls draw decal. But for every object, we want to draw them centered, right? So let's do an exercise. If we wanted to put this in the object class, will we put it a draw function in the player and the enemy? Or would we put it in the object class? We would put it in the object class, because both the player and the enemy need to draw stuff, and they need to draw stuff in the same way. So since it's shared, once again, we're going to make a function in the object class that handles the drawing for us. It doesn't have to be overwritten, because every object needs to have their sprite drawn on screen. So we're going to make a draw function that applies to every object. So inside of here, we once again define our draw function, and we are now going to draw a centered decal. So one easy way to center and draw according to direction is to use draw rotated, PGE's draw rotated decal. Draw rotate decal, this is pretty lengthy, but it will do our job. So it'll be based on our position, it'll be based on our image. We have to use the decal, so we're going to call image dot, it should be image dot decal. Oh, make sure this is the object's draw function there. That way you get access to your parameters. So the image's decal, we have to specify an angle. So that's our direction. we have to specify the center. So we're going to have the center be our sprite's center. So one cool thing we can do is we can look at our sprite, and then we can get the, I believe it's the size function, and we divide that by 2, and that'll give us a center where, well, everything's centered. So this is now our draw function for every object. And finally, inside of polymorphism.cpp, instead of calling drawDecal here for every object, we're now going to call object.draw. We're going to pass in this as the PG instance, and we're going to pass in felapse time as how much time has passed. Now keep in mind that by doing this, we made it so in the future we can come back to this draw function and add more for every object. You can see this pattern growing, and yeah, so you can actually see the enemy players are changing direction. We just haven't made them move based on that direction. So that's actually working now. And you can see all the sprites are centered now because I can go to the boundary and it puts my image gets cut at the center. So all the images are now drawn centered. We can go to this edge and see the same thing. So let's make our players move based on what their direction is. And once again, think about it. Does moving based on direction have to be for the player, the enemy, or the objects? Well, let's look at it this way. We made a velocity component, right? And so far, the player is just adjusting their position directly. What if instead the velocity component determines the movement, and we made the player slow down over time? What I mean by this is that normally when you're designing games, if you want to move, like to the right, you set some velocity, and then your position is influenced by that velocity. So when you have a velocity of like x5, that means you're moving 5 to the right. So every single frame, you move 5 to the right. So you go a little bit to the right, a little bit to the right, a little bit to the right, in increments of 5. That's what velocity is. And so if in our enemy update function, we were to say, set the velocity equal to our direction. So set velocities, x and y components. We're going to do this by using trigonometry, by the way, at least a little bit of it. It's a vector, so we can define its... sorry, is this supposed to be speed? My bad. I thought I called it velocity for some reason. Speed and velocity, same thing. The cosine of your angle and the sine of your angle multiplied by what you want the amplitude to be, or how fast you want to move, is how you get a directional component from your a vector from your direction. So how fast do we want to move? Let's move as fast as the player, so 32. That's going to be our direct speed. And we can actually multiply the 32 out here, like this. We just have to define that this is an OLC 2D vector. And then we can multiply by 32. It's just a built-in multiplication operator for vector 2Ds. So this is really cool, because if we define that we want to move to the right, then the cosine of 0 is going to be a positive, I think it's just 1. The cosine of 0 is 1, and the sine of 0 is 0. So it's 0 in the y component and 1 in the x component. And you can see here that works, because when we multiply by 32, we get a 32 velocity in the x component. And we can try one more, right? Let's say our direction was up. And up is, I believe... Crud, that's kind of hard to think about. It should be 3 pi over 2. So 3 pi over 2, the cosine of that is 0, and the sign of that is 1, or -1. And so that makes us move up. So just some fancy little trick stuff going on here, but it makes it very easy. However, we don't adjust our position based on speed yet, and we definitely don't do it for the player. So now, for the player, I'm actually going to change this. I'm going to set its speed components based on what we're holding down. So I'm changing this as well, so we can now utilize that. So by changing it to only have its speed components set to these, we can now influence the position inside of internal update here. So we can now set the position by adding the speed multiplied by f elapsed time, because we still need to be influenced by the frame rate, and that will move everything based on its speed component. Let's go ahead and run this now. So you'll see now all the enemies are moving based on the direction they are given. They can't go out of bounds because they're respecting the object's internal update boundary checking code, and we can also do the same thing. Now, one funny thing about me is that I'm not holding any keys right now, and I'm moving diagonally. Every time I press a key, I'm adding to my components, but I'm not removing from them. So one fun way we can deal with that is by making it so... Also, we can influence the direction, by the way. So we can say, to get everything rotating right, even the player right now, because we could set the direction as well inside of here, but I think it would be fun to set the direction based on our speed, right? So we can set our direction to be equal to the components of our speed. So we would figure that out by doing what's called atan2. atan2 is a function that figures out, I think, the tangent, but it figures out the tangent in a way where even if you go out of bounds of the tangent, it like wraps around. So it's a pretty smart function. And the way you define atan2 is by taking y over x. So it provides two parameters here, and we just specify the y speed component and the x speed component, and it can figure out the angle based off of that. Again, it's a little more trig stuff, but if you deal with that a lot, you will see that. So now you can see even our player, because we used that draw rotate decal function with direction, moves or rotates with that value. So the final thing we have to do now is make it so when we release the keys, we slow down. So we can add a parameter called friction, and friction, in my opinion, applies to all objects as well. So to keep our simulation happy, we're going to be adding a const, which means it can't be changed. We're just going to add some friction value. I like to capitalize these if they're const. That way I know they can't be changed. And I'm going to make the friction be 100. What this means is if we don't apply any more speed to our objects, they're going to slow down based on this value. So every frame in internal update at the very bottom, we're going to subtract an amount of friction multiplied by f elapsed time. So we're going to have to do that for each component, but it's based on whether or not it's positive or negative. So if speed.x is greater than 0, we need to subtract. If speed.x is less than 0, instead we have to add. And we can do the same for the y components. By doing this, if we don't reapply a speed to our player, it's going to keep slowing down because the speed gets reduced by friction and our velocity is influenced by our player, by our speed. So you can see here the enemies now try to move, and then once they have moved a little bit, they stop. And if we hold right and let go of it, we eventually stop too because of our friction. Now, we originally wanted our players to keep moving and not stop. So because of that, we need to make it so our enemy keeps moving in a certain direction. So instead of setting the speed when move timer is less than or equal to 0, we're just going to have them constantly set their speed based on their direction, and just have their direction randomly change. So that's a quick fix. That way they're still moving like they did before. And now you see we get this interesting little rotating effect if we are turning between different angles. And that's just a side effect of us controlling our speed based on our vectors. Now you'll see every time when I release and stop, I end up pointing this way, in this direction. That's kind of a bug, because we kind of want it facing our previous direction, right? We don't want to completely stop. So one easy way to fix that is by not going negative here. We only want to go really low. Once we're too low, we don't want to go any lower. So we're going to say if speed.x is greater than 0, we subtract it, and then we say if it's less than 0, less than or equal to 0, how about we don't go all the way down? So let's say 0.001. We'll leave a very, very small component of it hanging around. Actually, we could just set to 0 too, I think. But we have to be careful. We have to, like, keep track of what our last direction was. This is more of a tricky problem to solve. Maybe you guys can figure out a way to really solve it. But we definitely don't want to go negative. I think that does make things really weird. Oops, don't do that. If speed.x is less than or equal to 0, make sure we set it to 0, which we can also shorten a little bit by saying, I'm not going to use the max and min here. I think that makes things a little more confusing, especially with all these signs being thrown around. I think this is more clear and simple to use. So I'm just finishing up here. If speed.y becomes greater than or equal to 0 after we've added to it, then we need to stop. Let's take a look. It should get us pointing to the right again when we stop. But again, you guys might be able to come up with a decent solution of this. The way I would do it is every time we press a key, we hold a previous direction variable. And so if we're stopping, set our direction to that previous direction variable, but don't influence it based on our speed. Here's another way you can do it. If speed.y is greater than 0, or not equal to 0, or speed.x is not equal to 0, right? Don't update our speeds as if one of these two are, or don't update our direction if both of them are 0. Voila. Magical. Also, you'll see our console still spammed with player object. I'm going to remove that now. We just had that there this whole time. Cool. So that's almost it. The last thing we wanted to do in our game, and it's probably the easiest one at this point, it just requires a little bit of fancy vector code, is we wanted to make it so when we collide with enemies, we actually destroy them. Another thing I'll point out is we can't tell the difference between players and enemies right now. But you'll notice I added a color parameter earlier. I think it's time to utilize that color parameter. So an object, we had, oh, I thought we had a color parameter. I guess when I came up with the original spec, I just forgot about it. Let's add a color parameter. So we're going to do that by specifying pixel color and OLC pixel color, excuse me. We're not going to define it by default, but we will define it when we create a player or an enemy. So let's go in player.cpp here, where we create our player. At this time, we're also going to set the color directly. So we'll set color equal to, let's choose the blue color for a player. And for the enemy, let's choose a red color. Let's do dark red, actually. You'll notice I didn't go in here and type in color OLC dark red, like this. We're not actually allowed to do this, because in here, you specify parameters that are going to be set when the object will be created. But the enemy class itself doesn't actually hold the color member, the object class does. So at this point, the object class has not been created. So you'd think you'd try to use this syntax, but you actually can't. You have to wait till the child class is created, and the current class you're creating has been made, and then you set all the variables in here. So this is kind of a subtlety, and why we have to put it inside of these curly braces. After we set our colors for each individual object type, we have to actually render it properly, because right now, our draw function does not take color into account. So that's just an additional property of draw rotated decal. I'm going to keep the scale at 1:1, but I'm going to go over to the tint parameter, which is currently set to white by default, and use the color to tint the player and the enemy. If I run the code now, after the player constructor and enemy constructor sets the color, you'll see our sprite is also influenced by that color. So the final thing to do is to make it so when we run into them, they get deleted. The way I would handle this in object-oriented programming is that every object might be in collision with every other object, right? And so you would iterate through, for each object, you would iterate through all the other objects and see if they collide. And the naive way to approach this, which is one I did in a previous example, was we have our 5 objects, right? Right now. We run a loop that iterates through each object. So we start at object 1, and we check object 2, 3, 4, and 5 for a collision. If we collide with all of them, any of them, then boom, we set a collision event for both objects. So let's say these two collided with each other, both of them receive a collision event. Note that we still don't know if objects 2 and 3 have collided with each other, or 2 and 4, or 2 and 5, and we don't know if 3 and 4 and 3 and 5 have collided with each other. So a proper collision event will make sure that all of these combinations can be met. So you have a starting marker, you iterate through all objects down the list, and then you increment the starting marker by 1, and you go again. Because you already know all of object 1 is taken care of. And then you increment the starting marker and go again. And this is a simple way to search for every object and see if they collide with every other object. A very naive approach would be to iterate through every object and then have another for loop that iterates through every object. But this would also mean you're going to be generating multiple collision events, which I don't think would be ideal. So that is how we're going to do it. So first off, every object needs a collision event, I guess you could call it, that can be overwritten. So we're going to make a new collision function, and the collision function will actually return what we collided with. So we'll include the object that we collided with. Collided object. Notice I include the virtual keyword here, that way we can override it. And since this is already basically an interface, we're going to require every object, every child, to override the collision function. So in both the player and the enemy header files now, we have to include that collision function as well. So I'm just going to copy that without the virtual keyword. By the way, you can declare these virtual in child classes. It doesn't hurt. That also means they can be child classes, which get overwritten as well. It can be a continuous chain if you really wanted to, but we're not going to handle that. So now that we included these, we're also required to update player.cpp and enemy.cpp with these collision functions as well. So make sure we define this is for the enemy, and define this, but for the player. And now that we've done that, we can say what we want to do when we collide. So we're actually not going to do anything for the enemy, we're just going to do it for the player. We need to mark them as dying or dead when this happens. So we don't have a flag that indicates whether an object's dead yet. So we'll go back to object.h and add another boolean, because any object can be dead. And we'll say dead is false by default. If the player runs into an enemy, so we'll say if collided object, it's a pointer, so we have to use arrow syntax, is not friendly. We don't want to run into friendly units, though we only have one friendly unit in this game. Then we want to set it to be dead. And we'll handle the dead flag a little later for actually getting rid of it. But for now, this just indicates, yeah, that object is going to die now. For the enemy side of things, we're not actually going to do anything, because we've already handled it on the player side. We just provide this here as a bonus, in case we wanted to do something on the enemy side when the player got hit, or when it hits a player. Finally, in onUserUpdate, we have to actually write our collision function. So we're going to be using that marker I indicated earlier. So this is the, I'm just going to call it the list marker. We're going to start from 0, and we're going to work our way through the list. So list marker is less than the amount of objects on the screen, so objects.size. We will increment the marker. Inside of here, we will set another marker. This is called the... We'll just call it the object marker. And we set it equal to the list marker. And then we will make sure that is less than objects.size and increment that marker. And that's pretty much the little collision algorithm I was talking about earlier. Whatever the list marker is at, that's where we start, and we iterate through all the objects and see if they collide with us. To find out if they're colliding with us, we need to know if one is touching the other. We didn't specify a radius here. I was going to use circle collision. So we're going to define a radius, and by default, I'm actually going to make it be 16. I already know the sprite is actually 8. I think the sprite is 16 by 16. I could be wrong about that. But we're going to make the default be whatever the image supplied was. So I'm actually going to go to object.cpp here, and when it's created, we're going to set, we can actually do it in here. We are going to set the radius to be equal to whatever the image's sprite's size divided by 2. And we only need the width. So let's actually use the width here. The width divided by 2 is going to be the default radius. If for some reason using the width is not the case, then we will override that with something else. But we'll say the default is to use the sprite's width, which should be 8. So we have to do a distance check here. So I'm going to write a little auto function, which I like to use especially for the distance formula. So I'll write a little lambda here, where we take the distance between 2 points. So I'll provide 2 vectors here, position 1 and position, I forgot OLC. Position 1 and position 2. Inside the distance function, we run the distance formula. So the distance formula is the square root of the squares of the differences of the x and y's of both components. That sounds like a mouthful. The sums of the squares of the square root of the sums of the squares of the differences of the components. Yes. Basically this. So I like to write these in a little lambda and return them. We can get rid of this now. We're all done with those. And that gives us the ability to find out the distance by calling the distance function, though, here. So we're seeing if the distance between the 2 objects we're comparing is less than their radii. That's basically circle collision. So just a quick recap. We got 2 circles here. Circles have radii, like so. If we were to take the sum of these distances and put them together, this distance here determines how much distance they have to be in collision with each other. So if the circles were like this, their radii, the distance between these two is smaller than their sums, and so they would be colliding. That's circle collisions in a nutshell. It's the easiest one to implement, and I use it very often with games because that's really nice. Technically, rectangle collisions are faster because they don't involve as many multiplication and division maths, but circle collision is just easier to explain and work with. So we don't have our objects yet, so we're going to grab pointers to those objects. So object 1 is taking the first marker and going through that list. So we say objects list marker gives us our first object. And then the second object comes from the OBJ marker, the second one we're inside of. Also, I forgot a semicolon over here. So let's appease the compiler. So we're now comparing object 1's position to object 2's position and seeing if that distance is less than the sum of their radii. So we add the two radii together. And we see if the distance is less than that. That means we have a collision. So then we'll send a collision event to both object 1 and object 2 containing the respective opposite objects. That way they both receive a collision event and they're notified of it. We can make sure this works by now adding an output message saying collided. Player collided. And we can say inside of enemies the same thing. We can say enemy collided. I go ahead and run this. Let's see if it works. So you can see right now there are a bunch of messages. Let's pause real quick. It actually says player collided in a couple of these, and that's a little troubling, right? Because we actually haven't collided with anything yet, so what's going on? You might notice player collided is happening twice. Enemy collided is happening exactly 4 times, which is the amount of enemies we have, or 8 times the amount of enemies times 2. You might be catching on that each of these is being executed twice. They're colliding with themselves. Every time you're doing this, make sure that you're not comparing the object to itself. So if list marker is equal to object marker, let's continue. We don't have to look at these set of objects then. That way, nothing's colliding with themselves. Because up until this point, we should only see enemies colliding with enemies. And once I go over to them, it should say player collided at some point too. So you'll see here now we're getting some player collided messages, no messages, player collided, no messages, so on and so forth. So we can tell that's kind of working. And now all we have to do is work with the dead flag, because we've been setting the dead flag every time we collided with an enemy, but we haven't done anything with it yet. So the final thing we have to do now is down here, we're going to use a feature of C++20. So I'm actually going to go into my project properties real quick, and I'm going to change the C++ language standard to use C++20. By doing this, we can now access a nice function I've come to love called erase_if. Erase_if requires a vector and a lambda containing what you want to do to determine if each object should be deleted. So this is a vector of object pointers. So I'm going to look at each object, and the times we want to delete them is when dead is true. So I'm going to say object dead. If that's true, delete it from memory. Let's see. Because now if we delete it from the vector, well, it's gone completely, right? Yep, sure is. Almost. There is one caveat to them being gone. Remember how we created these pointers here? These are raw pointers. I have another video where I explain how we turn this example we just made into smart pointers, so they'll be deallocated automatically. But if you're using raw pointers, remember to call delete every time you call new somewhere in your program when you're done with it. We have to now check if the object is dead, delete the object from memory and return true. Otherwise, return false. I think it's really important to explain that if you allocate pointers, you must delete them and clean up your memory. So we're going to pause real quick. I'm going to go to memory usage here because I want to take a snapshot of memory before and after we collided with something. So I'm going to add a breakpoint when we collided with an enemy, so it gets marked as dead. Let's go ahead and run into an enemy. So apparently we just hit an enemy. It looks like, yeah, during my simulation, it jumped an enemy up. So collision with object has now occurred. Okay, cool. So I'm going to go down here to right before we erase if. So I'm going to hit continue. Now we're here. I'm going to take a snapshot of memory at this point in time. Actually, I need to redo the profiler. My bad. So we'll go through this one more time. So restart the game. Don't do this. And let's collide with an enemy. They're all kind of wandering on the edges right now. That's fine. Come here. All right, so we've collided with an enemy. We're gonna hit we're gonna make a breakpoint right here and hit continue. So now we're here. I'm gonna take a snapshot of memory at this time. We've done 5,047 allocations so far. I'm now gonna make a breakpoint going in here because once we go in, we're gonna find an object that might be dead. So we found an enemy that's dead and we've deleted it. We can see the number of allocations has gone down by 1. So we now know for sure that that just deleted it from memory. And this is going to be explained in more detail in my smart pointers video. Because in smart pointers, we go ahead and take this example and make it so we use smart pointers, which automatically remove themselves from memory. So if you liked this example and want to learn more about how to make this example even better, do check out that video as well. I hope this has been helpful and showed you some insight in how we've been using some of the features of the C++ programming language to go from using single files to using multiple files to using object inheritance, which allows us to do cool new things and to handle objects in a new way, where the game only controls what's being called for objects, but the objects do everything inside their own files. It's all split up very nicely. And I think this is the first time I'm showing us splitting up the Pixel game engine into multiple files. So that's very handy too. If you have any questions, feel free to contact me on my Discord, or you can reach out in the comments as well. I hope this helps, and keep a lookout for future videos. Take care.